We're going to take a look at the concept of local linearity, and if you're in my class, this is a concept that we are revisiting. We've looked at the idea of local linearity before and how it relates to differentiability. But as a reminder, you can see, if you have my packet, you can go to this page in the packet. Local linearity is a property of many functions that can be used to approximate the function by its tangent line. So I want you to take a minute to go back and reread that statement, because ultimately that is our goal. You can see the objective is to identify local linearity, but even further than that, we're going to use this property of local linearity to approximate the function by its tangent line. So what does that mean? What is the real objective here? Well, what that really boils down to is that we're going to use the tangent line at a given point to approximate y values of the function. And when I say the function, I'm talking not the tangent line, the given function. So we're going to use the tangent line at a given point to approximate y values to the function that are very close to the point of tangency. Now that's not going to be fully apparent as what we're really trying to do until we actually jump into a problem. But when we do the problems, come back to this statement, and at the end it would be good to come back to this statement to remember, what are we trying to do? We're going to use the tangent line at a given point to approximate y values of the function that are very close to the point of tangency. And that very close is important. That's the whole idea of local linearity. Alright, so the second statement that you see here is linear. Near any point, and again a key word is near, very close. Near any point, the graphs of most functions look like a line whose slope is the derivative of the function at the point. We in class have taken functions and we've zoomed in and zoomed in and zoomed in at a particular point on a graph to see whether or not the function becomes locally linear. Local, this property holds only on a small region or a neighborhood of the domain of the function. So for example, if you take a look at the curve that I have here, I'm going to try to trace this in blue. So there's the given curve, and what you see dotted here is a tangent line. Now the point of tangency is here, and so my dotted line, this is the tangent line, and the blue is the given curve, and I'll just call that, let's see, do they name? Yeah, they call it, the curve itself is f of x. So red is tangent line, blue is f of x, and I'll call tangent line y, because that would be the name of my line if I were to write the equation of that line. Now what I want you to think about, the function, the blue function and the red tangent line at 1 have a point in common. So they've given us the value of 1. In other words, f of 1, that's the blue function evaluated at 1, is equal to y of 1, that's the line evaluated at 1. That is the point of tangency. They share that point. So at that particular value of x, at 1, the tangent line and the curve are in common. They share exactly the same y value. Now the idea here is, let's say that we did not have the curve. So we don't really have a way to erase this, but if we took away the function and all we knew was the equation of the tangent line, could we get y values on the function? Well, it depends. If you were to look in this little neighborhood, let's say right around here, if we were to use the tangent line to approximate y values of the curve, then those y values would be very, very close. There would be very little error. Now, if you come out here to this point that they've highlighted right here, and here is the y value on the given curve at this particular value of x. I'll call it c. So at x equal to c, f of c is not equal to y of c. In other words, the output of the blue curve is not equal to the output of the red tangent line. They're not equal. And furthermore, there's quite a bit of error in here. So I would say that the tangent line would not be a good approximator of y values for the blue curve. However, if you move into this little neighborhood here that we were just talking about, so for example, if I didn't know the equation of the function, could I use the line, the tangent line, y, whatever that happens to be, 1.001, would that be a good approximation of f, the actual function value, at 1.001? Well, yeah, I think that would be a very good approximation because in this neighborhood, the tangent line is very close to the actual curve. So I could approximate the y value at an x value very close to the point of tangency. Now that's the big picture idea. That's the overview of what we're going to do, but we're going to look at some particular examples that I think will help make this a little bit more clear. Alright, so on the next page, if you have this packet, you'll see this problem, and it asks us to use our graphing calculator to graph the function, which I don't think we have to do that because the function's already given to us. So let's see what we're being asked to do here. We have a square root function, and job number 1 is to find the equation of the line tangent at x equal to 4. So, equation of the line tangent to f at x equal to 4. So here's x equal to 4, so the tangent line would look something like that. Of course, if you're drawing this yourself, you use a straight edge so that you can see it, get a better picture of the tangent line. So the function here, let me go back to my blue, the function is f of x, and the tangent line equation that we're going to write is y. So remember, when we're writing the equation of a line, the standard form is y minus y1 is equal to, well, it's not standard form, it's point slope, x minus x1. To find the slope, we're going to need to find the derivative of the function. So I'm going to go back up here. So on my blue function, f prime of x, the first derivative, would be 1/2 of x minus 3 to the negative 1/2 power. The derivative of the inside is 1, so I don't have to worry about that. So the first derivative, if I clean it up and I move things around, would be 1 over 2 times the square root of x minus 3. I need the slope at 4, so I'm going to evaluate the derivative at 4. So f prime at 4 would be 1 over 2 times the square root of 4 minus 3. 4 minus 3 is 1. The square root of 1 is 1 times 2 is 2. So the derivative at 4, or the slope of my line, is 1/2. Alright, so let's start filling in our information here. We have y minus, we don't have the y value yet, so let's go back and calculate that. So we're going to need f of 4. If we put that into the original function, that would be the square root of 4 minus 3, which is the square root of 1, which is 1. So we have the point 4, 1. And that's the point, we can see that from the graph here. This is the point 4, 1. And the slope of the tangent line, or the derivative at 4, is 1/2. So we have y minus 1 is equal to 1/2 times x minus 4. If you want to clean that up and get y by itself, you would have y equal to, let's see, 1/2 x. Half of negative 4 would be negative 2, plus 1 would be negative 1. Hopefully I did that correct, so let me check that again. 1/2 x, that would be negative 2, and then we're going to add the 1 to both sides, so that would be, alright, so I have y by itself. Really doesn't matter what form we leave the equation in. Alright, next question. So we have the equation of the tangent line. Next question. Describe the proximity of the line to the curve near x equal to 4. Well, we talked about that a little bit already. If we go in that little neighborhood, the line is very close to the curve. I don't really know what else to say. In the proximity of the line near the curve is that the line is close to the curve, and therefore if we're very near to x equal to 4, the line is a pretty good approximator of y values for the original function. Now it says zoom in at the point 4 f of 4 3 times. How are the line and curve related? I'm not going to do this right now, but basically what they want you to do is in your calculator in y number 1 put the original function f of x, and in y number 2 put the equation of the line, and they say zoom in 3 times, and what happens, as we've already done this in class, the curve and the line seem to assume one another. They coincide, so to speak, because you were very, very, very near that point. And you can do that on your own if you want to go back and refresh that. Letter D says we say that f, the original function, has local linearity at x equal to 4. In other words, the function f of x, which is a square root function, becomes linear as you zoom in. So what appears to be a curve globally, when you zoom in and you get this really, really small window, and there's you haven't moved far away from the x equal to 4, the curve looks like a line when you zoom in, and that's that whole idea of local linearity. Globally a curve, locally linear. All right, problem number 2 is a problem in class that we have looked at before. It's an absolute value function, and when we did this in class, you'll recall that, well, first question, is g, the function that's given here, locally linear at the point 1, 2? Well, we already know from, at least from our class, that this function g is not differentiable at x equal to 1 because there is a sharp turn. Now, that's not how I would defend myself with calculus. What this really has to do with is that the derivative on the left-hand side of this point has a slope of -3. The derivative on the right-hand side of this curve has a slope of +3, and these two slopes are not agreeing with one another. The derivative on the left-hand side is not equal to the derivative on the right-hand side. Furthermore, if you zoom in, if you go to the point on your calculator 1, 2, and you keep zooming in and zooming in and zooming in and zooming in, what you'll notice is that the function does not become locally linear. Therefore, there's no derivative at x equal to 1, 2, and we can't write the equation of a tangent line. All right, so that answers those two questions. Now let's get to the business at hand. What are we trying to do here? Well, we have a graph of a parabola, and it's already shown below. We're to find the equation y for the linearization. Now, don't be freaked out by the word linearization. Look at this root word here. In other words, linearization means write the equation of a line for the given function at x equal to 2. So we're focusing in on x equal to 2. We want to write the equation of the tangent line. Let's see if I can draw that without missing. Not quite. You get the idea. All right, so we want to write the equation of this line, and we are tangent at x equal to 2. So just like we did before, we're going to need the derivative of this function. So f of x is equal to 1/2 x squared. So f prime of x would be 2 times 1/2 is 1. So f prime of x, the first derivative is 1. We're going to need to evaluate the derivative at 2 in order to get the slope. So we get 2. We also need the y value of the function. So if we go back to f of x is equal to 1/2 x squared, we're evaluating the y value at x equal to 2. So 2 squared is 4, and 1/2 of 4 is 2. So we have the point 2, 2. So on my graph, I have 2, 2, and I know the slope of the tangent line also happens to be 2. I found the derivative, substituted in the x value. So to write the equation of my line, I'll have y minus 2 is equal to 2, which is the slope, times x minus 2. If I get y by itself, I will have 2x. That would be minus 4 plus 2. 2x minus 2 is the equation of my tangent line if I didn't make any error. Okay? So I have the equation of the function. I have the equation of the tangent line. Now keep in mind that in this neighborhood, the line is a good approximator of y values for the original curve. So that's what they ask us to do in letter B. They're saying approximate the y value. So find f of 1.7. F is the original function, the parabola, approximated using y of 1.7. In other words, I'm going to put 1.7 into the equation of my line. Okay, so I also want to put that equation into my calculator. I already have the parabola in my calculator, so I'm going to put the equation of my tangent line, 2x minus 2. And let's take a look at that in the calculator. All right, so you see the same thing that we're finding here. I'm going to do a second calc value 1.7. Let's see. That's telling me, now you have to be careful, that's y1. So 1.445 is the actual real deal y value on the curve. Now, if you arrow down to the tangent line, you see that the output is 1.4. Okay? So, the tangent line is a very good approximator of the real deal y value. This is an approximation, and I was using the equation of the tangent line for the approximation. Now let's go back to the calculator, and let's do something here. View, always on top. All right. So if I go back, arrow up to the real deal y value, the real deal y value is 1.445. So the next question says, what is the error? How much difference is there in the approximation versus the real deal? So they tell us to calculate that error. Well, this is kind of common sense. They said the expected value, which is the actual value, 1.445, minus the approximate value, 1.4. And you can see, let's see, I lost something. Oh, I put an extra. Nope, no, I'm good. So we're finding the absolute value of that. So if we go back to the home screen, 1.445 minus 1.4 gives us an error of 0.0445. In other words, there's not much error. There's not much difference between those values. So the equation of the tangent line could approximate y values very, very close to the point of tangency. Now, if you go to your table, and that's kind of the next thing that they're going to ask us to do, is they want us to actually look at approximating y values very close to 2. So in this column, the f of x, this is the actual function. That would be the parabola. And this y is the tangent line. And so I'm just going to use my calculator to do that, except you'll be careful because my two tables are going to be switched because I have my original function in y1 and my tangent line in y2. So if you come back up here or look at my calculator, y1 is the parabola, y2 is the tangent line. if you go to your table set, I don't know if you're familiar with your calculator or not, so I'll walk you through this. You can set the calculator where I have independent, you can set that on ask so that you can ask for specific values. I've already set this up in my calculator, and then when I go to the table, you can see, now remember my y number 1 was the actual function. Oh, it's the same way they have it. Y number 1 is the actual function. Y number 2 is the equation of the tangent line. And by subtracting these values, you can see how much error there is. There's also some other interesting things that you can see here. We have this whole idea of limits as x approaches 2 from the left, and as x approaches 2 from the right, we're approaching a y value of 2. So the limit exists. You get the whole idea of local linearity. You get the whole idea of derivative, because as you get closer and closer and closer, the slope at the tangent line is equal to the slope of the curve at that point. But if you were to calculate the errors, and you can do that by filling in the table, I'll let you figure that out, there's not much difference. So the big idea, again, is that the tangent line, this equation y, can approximate y values of the given curve in that little neighborhood. You don't want to approximate them for 3 and 4 and 5 and 6 and 7, because the error becomes greater as you move away from the given x value of 2. What do you notice about the error as x approaches 2? The error decreases. Is the approximation too large or too small? Well, let's go back to the graph. Notice, and this is going to be very important, notice that the tangent line is below the curve. Why? Because the curve is concave up. If the curve's concave up, the tangent lines are going to be below the curve, which would always mean, so we'll say, therefore, 3 dots in the shape of a triangle, therefore, the approximations would be too small. Because if the line is below the curve, then the y value outputs are going to be below the y values of the curve. The only place that they coincide is at the point of tangency. So anytime I use this tangent line to approximate y values on that curve, the approximation would always be too small, because the curve is concave up and the tangent line is below. So these three things are kind of going together. If the tangent line's below, the curve's concave up. If the curve's concave up, the tangent line's below. If those two things happen, the approximation is too small. Now, contrary to that, or opposite of that, would be if you have a curve that's concave down, the tangent line would be, whoops, I missed that. The tangent line would be above, and the approximations would be too large. So the curve would be concave down, the tangent line would be above, the approximations would be too large. It's like Goldilocks, except we don't get just right. At the point of tangency, I guess we're just right. All right, one more example. We have another square root function, and we want to find the linearization. Again, don't be afraid of the word linearization. The root word is line. It means find the equation of a line at x equal to 3, and sketch. Is this the curve that we had before? Oops. Square root of x minus 3. Oh, no. All right, so the linearization means write the equation of a line. Y minus y1 is equal to m times x minus x1. I'm going to need the derivative, so g prime of x is 1/2 x plus 1 to the negative 1/2 power. By the chain rule, the derivative of the inside's 1. So that's g prime of x is equal to 1 over 2 square root of x plus 1. The derivative evaluated at 3 is 1 over 2. 3 plus 1 is 4. Square root of 4 is 2 times 2 is 4. So we get 1/4. I did that fast. Let me make sure. 3 plus 1 is 4. Square root of 4 is 2. 2 times 2 is 4. So that is my derivative, which is going to be the slope of my line. Over here, I'm going to find the y value, g of, I would encourage you to do this problem ahead of me and then go back and check yours to make sure you know what you're doing. So 3 plus 1 is 4. The square root of 4 is 2. So I have the point 3, 2. So the tangent line would be y minus 2 is equal to the slope of 1/4 times x minus 3. All right, the next thing it asks me to do is to compute the square root of 3.98 with my calculator and compare this answer with the linear approximation from above. Now, when they ask us to compute the square root of 3.98, this is a little bit of a tricky problem. Not sure why they wrote it this way. Remember that g of x is equal to the square root of x plus 1. So if they're asking me to compute the square root of 3.98, then that means x was equal to 2.98, because 2.98 plus 1 gives me 3.98. So not really sure why they're asking me to do that, or asking us like that. Compute the square root of 3.98 with your calculator and compare this with the linear approximation of g of x from above. And then they want us to calculate the error in the linear approximation. So in other words, we're going to find y of 2.98. Again, I don't know why they're trying to make it confusing, but this over here, you can see why we're using 2.98. So I'm going to substitute 2.98 in place of x. Y minus 2 is equal to 1/4 of 2.98 minus 3. So let's see what we have here. So 2.98 minus 3 divided by 4 plus 2. So the approximation y of 2.98 is 1.995. Now all I did was substituted the 2.98 in here, and I did the calculations on my calculator, subtracted 3, divided by 4, and then added 2 to the other side. Calculate the error in using the linear approximation to estimate g of 2.98. So the actual g of 2.98, so the square root of 3.98. In other words, what I'm looking for is the actual y value on the curve. It's actually 1.994, because 3.98 is almost 4, so you expect the square root to be almost 2. So if we do 1.995 or 99499 minus 1.995, so minus 1.995. Oops, I forgot the decimal point. Let's do that again. Alright, so the square root of 3.98 minus 1.995 is negative 6.26 times 10 to the negative 6, which is really, 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 really small. So the tangent line can be, or is, a good approximator of y values very close. Now this line is tangent at 3. So the question is the approximation too large or too small? Well, look at the concavity of the curve. The curve is concave down. Therefore, the tangent line would be drawn above. Therefore, the approximations would always be too large. So it really has to do with the concavity and where the tangent line is with respect to the graph. So the approximations will be too large, and we already said why. That was up there on the graph that I just drew. And letter E, do not worry about. Now if you're in my class, I want you to go ahead and finish the pages in this packet. It won't take you very long if you understand this concept. Revisit the video as needed.